Greetings. My name is Elizabeth Wade. I teach basic calculus in the mathematics department at Pellissippi State Technical Community College. This is topic 5 on integration and segment 5.7 on area. In segment 5.5, we saw the area under a curve is related to the definite integral as follows. If f of x is a non-negative continuous function on the closed interval from a to b, then the area under the graph of this function can be represented by this expression, where each of these terms, f of x sub 1 delta x, represents the area of a rectangle that we would subdivide this interval into. And we would take the limit as the number of rectangles approaches infinity. And this expression we refer to as the definite integral. And this in turn is equal to f of b minus f of a, which the fundamental theorem of calculus states, and we looked at in the previous segment to help us evaluate a definite integral. Let's find the area under this curve, this function, on the interval from negative 1 to 2. Okay, so negative 1 is right here. I'll drop a vertical line. 2 is right here. And I'm going to shade the region that I'm finding the area of. This is negative 1. This is 2. So we would be integrating from negative 1 to 2 the function x to the third minus 2x squared plus 6 dx. When we integrate x to the third, we get x to the fourth over 4. Integrating 2x squared, we get 2x to the third over 3. Integrating 6, we get 6x. This is to be evaluated from negative 1 to 2. The fundamental theorem of calculus said to substitute the 2 in place of the x first. 2 times 2 cubed over 3 plus 6 times 2. Evaluate this. Then substitute the negative 1 in, negative 1 to the fourth over 4 minus 2 times negative 1 to the third over 3 plus 6 times negative 1. Evaluate this, subtract the results. If you do the arithmetic that this involves correctly, you end up with 15 3/4 or 15.75. Let's switch to our calculator and take another look at this problem. I want to show you another calculator function. So what I'm going to do is go to the y equal menu and type in our function. The function we were working with was x to the third minus 2x squared plus 6. I've also set my calculator window for the x values from negative 3 to 5 with a scale of 1 and the y values from 0 to 10, and I put a scale of 10. Now let's graph this function. And then what I want to do is go to second, calculate, calculates above trace, and I'm going to select this last choice, number 7, the integral of f of x dx, that's visible on the screen. So second calculate, number 7. It asks for the lower limit of integration. Well, our lower limit was negative 1. Press enter. And then it asks for the upper limit of integration, which in this case was 2. Press enter. And watch what the calculator does. It shades the region and it gives you the area of the region, which was 15.75. If you're not interested in seeing the graph, remember you can always use Math 9 to obtain 15.75. But this is neat because it includes the graph. Now let's go back to our notes and look at some other situations. For the above problem, we assumed that f of x was non-negative. We're now going to drop this restriction and focus on a more general situation of finding the area of a region bounded both above and below by the graphs of functions. Our rule states that on a closed interval from a to b, the area between continuous functions f and g is given by the definite integral from a to b, curve on top minus curve on bottom, dx. Let's look at a problem. Suppose we wanted to find the area bounded by f of x equal the linear function 2x plus 8, which is this graph, and g of x equal negative x squared plus 4, this quadratic function, on the interval from negative 3 to 2. So in other words, we're calculating the area of this region. Notice that part of this graph or part of this region is underneath the x-axis. Well, according to the rule, we would integrate from negative 3 to 2, curve on the top, in this case the linear function is on the top, 2x plus 8, minus the curve on the bottom, which is the quadratic function, negative x squared plus 4, dx. I would simplify this first, so the integral from negative 3 to 2, if you simplify this, you get x squared plus 2x plus 4 dx. Integrating x squared, x cubed over 3. The integral of 2x is 2x squared over 2. The 2's would cancel. That would be x squared. The integral of 4 is 4x. Evaluated from negative 3 to 2. According to the fundamental theorem of calculus, we substitute the 2 in first, 8/3, plus 2 squared is 4, plus 4 times 2 is 8, and subtract from that the result of plugging negative 3 in. Negative 3 cubed is negative 27 over 3. Negative 3 squared is 9, and 4 times negative 3 is negative 12. And if you do this arithmetic, this works out to be 80/3 or 26.6 for the 6 repeats. Note that if you wanted to do this on your calculator, you can use math number 9, FNINT, where you would begin with typing in the function. You can type it in either this format or this format, comma, x, comma, lower limit of integration, negative 3, comma, upper limit of integration. And that should yield this same answer, 80/3 or 26.6. Let's look at a couple more situations. In the first problem, we want to find the area of the region bounded by the x-axis, x equal negative 1, so I'm going to drop a vertical line, x equal 4, drop a line, so this is the region. This region is entirely underneath the x-axis. So we set up our problem as the integral from negative 1 to 4. Now, for the curve on the top, that would be the x-axis, and the equation of the x-axis is y equals 0. So I'm going to go 0 minus the curve on the bottom is the minus x squared plus 4x minus 6 dx. So we're integrating from negative 1 to 4. Since we're subtracting this function, the signs would switch to x squared minus 4x plus 6 dx. If you want to complete this integration using the calculator, I would recommend math number 9. Type in this function, the variable x, the lower limit negative 1, the upper limit 4, to obtain the answer, which is 21 2/3. Or you can integrate by hand. In the second situation, we want to find the area of the region bounded by this cubic function f of x and the linear function x plus 3. Well, notice that this bounded region is in two pieces. So our first job would be to use our calculator, graph the two functions, and find these points of intersection. This point of intersection on the left is negative 2, 1. This point is 0, 3. And this point on the right is 2, 5. So negative 2, 2, and 0. So when we set up our integration, we actually have to do this integration in two parts. First, we find the area of this region on the left from integrating from negative 2 to 0. And the curve on the top is the x cubed minus 3x plus 3. And we subtract from that the curve on the bottom, which is the x plus 3. And this, of course, is integrated with respect to x. So we get that answer. If you do this integration, and you can work it on your calculator, or you can simplify this and then obtain the integration by hand. This simplifies to x cubed minus 4x. And you're integrating from negative 2 to 0 dx. This turns out to give you an area of 4. And then in a likewise manner, you integrate to find this area of this region, but the difference is that the area of this region is found by integrating from 0 to 2, and the curve on the top now becomes the linear function x plus 3. And we're subtracting from that the curve on the bottom, x cubed minus 3x plus 3. And so in this case, we end up integrating from 0 to 2, and if you simplify this, you have minus x cubed plus 4x dx. So again, you can do this by hand, or you can do it on your calculator using math number 9, and you get 4 for the area. So the total area of these two regions combined would be 8. Well, that's it for this segment. Now you need to practice this concept by working similar problems. Good luck.